Hi, I'm Kevin, and I invented this, a desalination device. You see, water's pretty important, but we're running out, fast.
My research aims to fix that. So instead of relying on massive reverse osmosis plants that cost billions and run on fossil fuels, my device is cheap, portable, and solar powered. Let's look at how it works. My invention can be cut into three parts: solar energy, the multistage, and the hydrogel. My research is solar powered, and in order to capture as much energy as possible, I basically built a satellite dish, covered it in mylar, stuck it on a pair of rotating arms mounted to a turntable, and by using 3 photoresistors, I can not only track, but also follow the sun. All of this solar energy then gets focused through a lens onto a heat pipe, which then heats the multistage of hydrogels below. The multistage aspect of my design is simple. If you've ever watched a kettle boil, you'll know that hot steam comes out the top. However, where most evaporative desalination techniques just condense and collect this steam, MIT used a multistage design to recycle the steam's heat and increase the heat efficiency by up to 400%, meaning that you're now getting 4 times as much water for the energy you would have put in before. Taking inspiration from this, I was able to use semi-permeable membranes and a corner-oriented collection system to make the system vertical. In addition to this, I made the stages out of silicone, due to its low thermal conductivity, high temperature endurance, and natural sealing ability. I simply printed the molds and poured the silicone. In addition to this, I made the semi-permeable membrane layer by 3D printing PETG as the lower clamp, cutting Gore-Tex as the membrane, and cutting acrylic as the upper clamp. Then glue it all together and you have the layer. Next, I cut out the aluminium squares and then pasted both the Gore-Tex layer and the aluminium into the silicone. Multiply that by 10 for all 10 stages and you have your multistage. However, another big difference is where MIT used capillary wicks, I used hydrogels, capable of halving water's evaporation enthalpy. How? Well, the hydrogel is effectively an interconnected crosslink of hydrophilic molecules, which, in this case, are chitosan and PVA. Leaving us with a hydrophilic crosslink which will bond with the water, pulling it outwards. The free state of water will then pull back, weakening the hydrogen bonding in this area, halving the evaporation enthalpy of water. In order to make these hydrogels, we first need some deionized water. Add some hydrochloric acid, pour in some PVA, add a little chitosan, and sonicate it overnight so it's homogeneous. Next, we add a little glutaraldehyde as a bonding agent, and set the solution in a mold, which I built in an engineering lab. Then, after the hydrogel is set, we freeze. Now, the research paper I'm basing the hydrogels off of used liquid nitrogen for freezing. However, I only have access to a negative 80-degree freezer. In addition to that, previous research used a freeze dryer, and since my school doesn't have one, considering they are so expensive, I tried to dehydrate them in a ventilated incubator, which ultimately failed both on a structural and microscopic level. So I decided to build a freeze dryer. The whole point of freeze drying is going from a solid to a vapor without going through the liquid phase. We want to skip the liquid phase. The way we can do this is by starting at negative 80 degrees at around 1 atmosphere. Then, by using a vacuum, we can plunge down and then safely cross into the vapor by slowly heating up. In order for us to make a freeze dryer, we need 4 things: a vacuum pump, the sample chamber, a water trap, and a cryo tank. The purpose of the water trap is so that the vapor being pulled off the sample freezes in the trap. You do not want water getting in the vacuum pump. So, I got a vacuum pump from the physics lab, bought the water trap, the sample chamber, and the cryo tank online, and then I got styrofoam for the insulators. Measured everything out, cut it up, and then glued it all together. And did it all over again for the second one. Next, I needed to connect the pump to the water trap lid. So I got a tap, drilled a hole, and then tapped the lid. Then I filled the cryo tank with water and left it in the negative 80 degrees Celsius freezer overnight. After that, I put it all together, put it in the frozen sample, and let it run. And boom, freeze-dried hydrogel. And as you can see, there are differences on both the structural and microscopic level to the dehydrated hydrogels. Additionally, as predicted in a separate study on medical hydrogels, the pore size is related to the freeze-drying temperature. As seen in this study, LaH4 when frozen at negative 80 degrees Celsius has much larger pores than LaH4 when frozen in prior research at negative 196 degrees Celsius. In the future, I plan on investigating the effect of the differing pore sizes through the use of calorimetry to approximate the vaporization enthalpy of my hydrogels versus others. And then, additionally, I plan to apply for DoD funding so I can build a field-ready product. And that is my research project. Thank you for watching.